So it's a great pleasure to be here. I'd like to thank the organizers for having me speak in this session. I'd like to do some review and tell a little bit about our own research in an area that's up and coming for the last decade or so, where people are trying to manipulate optical resonances in high-index dielectric nanostructures. So before I start, I want to acknowledge many of the people in my group that worked on some of the projects. You will see funding from several agencies and also from Samsung, and several very fun collaborations with groups at Stanford, the Technion, and also at KAIST. What I will tell you about is shown here in a field plot that shows you how light can interact, normally incident from the top, with tiny little optical structures that have a high refractive index. Think of semiconductors or high index dielectrics. And when you shine light on them, due to the circulation of the light in these high index materials, essentially by total internal reflection, you can store energy and manipulate fields inside these structures to manipulate fundamental processes such as light scattering, absorption, transmission, reflection, etc. So let me start you where I started in the nanophotonics world, and that was reading about Michael Faraday's famous paper, who was studying at the time the optical properties of tiny little gold colloidal particles that are in this vial over here. These colloidal gold particles are still in suspension, although they were made by Faraday. It tells you the stability, and the beautiful red color here is derived from how the way in which light interacts with very small, in this case, gold nanoparticles, where it drives collective electron oscillations very efficiently at a surface plasmon resonance, which causes spectrally dependent absorption. Now, interestingly enough, people have gotten much better over time, and here are examples of colloidal suspensions of different types of gold nanoshells, where the geometry of the shell and the size and the shape can be tuned to get very strong light absorption all across the visible spectrum and beyond in the infrared and mid-infrared. And I was intrigued that people had gotten this control over light-matter interaction, and especially when one of my students at the time, Lin Yu Cao, showed me a nice optical observation of a range of silicon nanowires, all the way here down in sizes of about 30 nanometers, up to 180 nanometers, as viewed in dark field light scattering and a regular optical microscope by shining white light on them. And you can clearly see that in this case also semiconductor nanostructures in sizes, 30 nanometers, that are much smaller than the wavelength of light exhibit very strong light-matter interaction. And I'll tell you more about how you can shape, engineer these resonances and use them in real devices. There's a little bit of history to this, or actually a lot of history to this. Arguably one great place to start is the work by Gustav Mie, who already discussed how light would interact with dielectric spheres, and from there in the 1940s to 60s, and later in the world of metamaterials, and we have many pioneers here in the audience, people started looking at how light interacts with not just a single sphere, but arrangements of spheres in or high index spheres in a dielectric environment. And there's a key paper by Lewin in 1947. Then there's, I guess, beautiful papers on sort of the design, the shape engineering of such resonators, especially in the RF. This is a famous paper that discusses many of the resonant optical properties of high-index dielectric nanostructures. And later on, people expanded their views and got fancier in trying to make artificial dielectric media composed of these high-index structures. Of course, there are many more papers in here that I'm missing, but these have certainly played a key role in the field. And right now, we're in a regime where people over a whole frequency range from the visible to the RF with many groups involved, try to manipulate, understand, and see how they can exploit nanotechnology in trying to control light-matter interaction in high-index semiconductor structures. So this field is starting to shape up as a wonderful, nice brother to the field of plasmonics, where we can now manipulate both optical resonances in metals and high-index semiconductor structures at the scale, which is essentially the scale of chip technology. So let me give you my simple-minded view of why I think it's exciting. In the chip electronics industry, for example, people have been able to scale down from macro-scale devices that you could see with your own eye to truly nanoscale chips with features, dimensions of metallic interconnects and semiconductor devices that are truly on the tens of nanometer scale, but perhaps not fully realized by the electronics engineers. The optical people certainly have been realizing that if you go from macroscopic materials, metals and semiconductors that look nice and shiny and reflective at the scale much bigger than the wavelength, if you shrink them down, you get these unique optical resonances in metals and semiconductors that have a little bit different origin, but should definitely and can definitely be used to enhance the performance of a variety of optoelectronic devices. So let me tell you a couple benefits of semiconductor nanostructures that are the same as metallic nanostructures. And that is the tunability of optical resonances, but also if you, for example, place two semiconductors, in this case silicon nanostructures, close together, you can shine light on them and get very high field intensity between the particles, very similar as observed between two tiny metallic nanoparticles. And these field enhancements are not as high, but pretty close to those of that you can obtain with metals like gold and silver. So light manipulation and high field concentration, two of the trademarks of plasmonics, you can do with semiconductors too, but there are a lot of additional advantages if you can manipulate light in semiconductors. For example, ohmic loss, that's typically considered a bad thing in plasmonics or metal optics, can be basically removed if you operate with photons that are above the band gap of the semiconductor that you build your nanostructures off of. You can also use, with higher energy photons, the fact that you can absorb light and create very high, long-lived carriers, much longer lived than in metals, where they typically relax and form heat. Here you can use these carriers and extract them at electrodes to, for example, make detectors, or let them move to active light-emitting regions and make optical sources. There are interesting new fabrication techniques and mature fabrication techniques for semiconductors, like CMOS technology, with which we can make all of these nanostructures. We can do band engineering inside the semiconductors, make things that have optical and electronic functions at the same time by creating PN junctions, quantum wells, etc. in the semiconductors. We can gate carrier densities inside semiconductors. This is very hard to do with metals because of the very high carrier density, 10 to the 23, 24 per cubic centimeter. Here we only have something like 10 to the 19, so we can manipulate and tune resonances. And we can, I guess, use these mobile carriers not only by doping, but also by electrical gating. So many flexibilities are offered by semiconductor nanostructures in addition to what one traditionally has thought about with metals. So let me tell you a little bit about the basic physics of how these resonances occur in semiconductors, and that could start with a simple optical microscopy experiment where we take white light, we can control the polarization, send it into a dark field microscope objective, and we can collect the light towards a camera, and then we can take an image of a semiconductor nanowire. There's an SEM image of the wire next to it, and if it's sub-wavelength, it'll typically show a beautiful, nice color, in this case a yellowish color for this germanium nanowire, and you see an intensity scattering spectrum here that shows a peak in the yellow part of the spectrum. If I now tune the size of the wires. Then I can tune the size all across the visible, and I can take spectra again as a function of wavelength, and you can see that small wires tend to have resonances, strong absorption and scattering in the blue part of the spectrum, and as I go bigger and bigger, I can move the resonances to the red of the spectrum, and also for the very big ones, I can see multiple peaks occur. So where do these come from? And moreover, interestingly enough, if I change polarization, I can see different colors. For example, if I align my electric field transverse to the length of a semiconductor wire, which I'll call transverse electric, I see a reddish color. If I align the electric field along the wire, which I'll call transverse magnetic, I'll see an orangey color. And if I take spectra, I can see that in some cases resonances align, are degenerate between the two polarizations. In other cases, there are differences. So here's the simple physical intuition for the resonances that can occur, in this case, in a nanowire. Think of a large nanowire first, and I can imagine a ray tracing picture where light can come in. Some of the light can enter this high index nanowire and be trapped by multiple total internal reflections. And whenever I fit an integer number m of wavelength around the circumference of the wire, 2 pi r, where r is the radius, I get a resonance, because then light that just comes in can constructively interfere with the light has gone around once, twice, 3 times, etc. And by circulating light, I enhance the absorption, but I also can control the leakage, so the scattering out of the wire back out, by controlling the size and shape. So I have control over scattering and absorption, just like with metallic nanostructures. Well, of course, ray tracing is not that good for a deep sub-wavelength nanowire, but if you plot and solve for the optical modes for transverse magnetic and transverse electric excitation, then you can see actually that these modes resemble things that have 3 wavelengths around the circumference. This is the cross-section 2, 1, and here's 0 wavelength around the circumference. And all of these individual modes for the 2 different polarizations can be excited to enhance absorption. So these are the basic blocks we have to work with. Here's the simplest device that we made using such a nanowire. And in this example, on the left you see a schematic of a germanium nanowire hooked up between 2 electrical contacts in blue. We shine light from the top, and we measure the absorption in the wire by extracting the photocurrent from the wire. And the absorption is a direct measurement of how much light, or the photocurrent is a direct measurement of how much light gets absorbed in the wire. And here you see the SEM image of the structure, and the illumination spot based on the micron scale size here can be small compared to the distance of between the contacts. So we can really probe the optical properties of the wires themselves. So if we look at photocurrent spectra for 3 differently sized wires, you note that the photocurrent spectrum as a function of wavelength is very different for differently sized wires. Black here is a radius of 10 nanometers, blue is 25 nanometers, red is 110 nanometers. And just like with the absorption, you can see that the small wires tend to have the strongest peak in the absorption on the short wavelength side of the spectrum, and the bigger the diameter of the wire, the further redshifted the peaks are. And very big wires show multiple peaks, and each of these peaks, as I'll show you, can be associated with a well-defined me-like or high refractive index resonance. The reason that we think these are, at the time that they are really resonances, is that if you look at the intrinsic materials absorption here in the inset, absorption coefficient versus wavelength, that shows a nice monotonic decrease and a drop at the direct band gap of germanium. No peaks in there. However, as soon as we shape the structure in wire, then we see all of these peaked structures in there. So, of course, one can start thinking about where do these peaks come from, how can I think of the fact that a wire can enhance light absorption? Well, one is the way thinking of light circulation inside the wire. Another one is to plot the power flow around a wire, and you can actually see if you follow the power flow or the pointing vector, flow lines of the pointing vector, you can grab light from an area that's larger than the geometric size of the wire, an antenna effect, and through that larger area, the absorption cross-section, you can funnel energy into the wire and absorb it and enhance absorption overall. And you could look at real simulations of that absorption cross-section, or what I plot here in these graphs, the absorption efficiency, which is the absorption cross-section over the geometrical cross-section. And you can see for the spectra that I just showed of the photocurrent, now plotted in absorption efficiency versus wavelength for the small, a little bit bigger and biggest wire, that the absorption spectra in black nicely overlap the, in experiments in red nicely overlap the simulated absorption spectrum that we can calculate. And there you can see that you can actually get light absorption maybe 2 or 3 times higher than the absorption that you can get in an individual wire. And if you start making many of these measurements, you can start creating maps of the absorption efficiency versus the radius of the wire and the wavelength, and in there the red regions that have absorption efficiencies of up to something like 2, you can see areas where we get the right size to absorb very strongly at this well-defined wavelength. And you can see that these features tend to be linear bands, nicely mapping our intuitive resonance condition, that we need to get a resonance where we can enhance absorption exactly when we fit an integer number of wavelength around the circumference. So there's a linear scaling between the radius of the wire and the wavelength where we get the strongest light absorption. So then, just like in plasmonics, people started looking at different sizes and shapes and arrangement, and here just a couple of studies. These you've seen. Here's another one where we now go away from circular cross-section wires, but it turns out that square, circular, hexagonal, triangular wires all exhibit these resonances. So it's a general feature of every high-index structure to be able to confine light in a substantial way. Also, if we go away from the elongated structures and slowly shrink the length of the beams, then we can also, here's the dark field light scattering for those, you can also tune the absorption and light scattering spectrum or polarization. So there are different ways of manipulating the resonances, and you can get an extreme flexibility in terms of your building blocks by making complex arrangements of structures. One interesting example to us in the earlier days of this field was to try and look at the high index structures of properties of silicon carbide rods. So this is in the infrared regime. Silicon carbide, due to a phononic resonance, shows a very strong feature in the real part of the permittivity, where you can get both in the high frequency regime a negative index, and you can use plasmonic effects, for example, to do tip-enhanced spectroscopy in the infrared. Or on the short, in the blue part of this frequency diagram, you can get very high epsilons of a couple hundred. So high index structures that can exhibit these resonances. And these can be exhibited by the whiskers that are shown here in the bottom left, SCM. So we try to use this to try and manipulate thermal radiation. And here's one example where within an FTIR microscope, we could take both extinction spectra as a function of wave number or frequency, and also look at, when we heat up these little silicon carbide whiskers, the thermal emission from the whiskers. So the key point to take away here is that if I take an extinction spectrum here in the blue, at the region where silicon carbide shows these strong high epsilon, and the whiskers themselves show me resonances, I can actually see these peaks, and these peaks can nicely be identified with the me resonances of the silicon carbide whisker. And if I heat it up, then that's the red spectrum. I can actually obtain thermal emission from these Me resonances. So by having high-index nanostructures that show optical resonances, by heating them up, I can thermally emit just in these resonances, and you use the resonant properties of these whiskers to control at what frequency I emit thermally, and also in what directions I will emit thermally. So going from individual whiskers, one can go more complex, and that's more recently what's happening. Here's an example on the top of an optical microscopy image in dark field, white light illumination, of two wires that lie close together. And in region 1 and 3, there's a wire just by itself, but in region 2, here's the SEM image, you have two equal-sized wires that lie close together. And you can see that in the region where they do lie close together, the color is different. It looks more yellow, and over here it looks a little green. And one can very simply, based on inspiration from chemistry, where people do linear combination of atomic orbitals, one can think about the interaction of light with the double structure by first understanding the individual nanowire modes. They look like, if you're a chemist, like SPD, or modes where you fit 2, 1, or 0 wavelength around the circumference. If you know the basic modes and you bring two wires together, as in the bottom right, then these two modes can form anti-bonding and bonding states that, not as in molecules have different binding energy, but in this case have different excitation energies. Resonant energies. So you can control the resonance frequency by changing the environment, either bringing in another emanator or actually changing, for example, the liquid around it. And that has formed in plasmonics some of the basis for plasmonic sensing. This will be the same beneficial thing over here with high-index dielectrics. Then many people became very creative in thinking, in part inspired by plasmonics and the RF of all sorts of other structures. Here, examples of beautiful work from the Kiefscher group in trying to make dielectric particle arrays that look like a dielectric version of a Yagi-Uda antenna that can generate directional emission, or arrangement of dielectric structures to get intriguing line widths in the scattering and Fano-type resonances, energy storage, or entire arrangements, as shown over here, arrangement of subwavelength dielectric scatterers to combine, in this case also, magnetic and electric dipole type modes in these structures to get very strong light reflection action, as strong as one might expect from a regular metallic mirror. Here's another most recent one where people arrange particles in a gradient fashion to try and redirect light beams, and I'll talk a little bit more about that. So this is a current high activity where people try to arrange using the knowledge of the individual resonator building blocks to try and arrange them in much more complex structures that provide increasingly complex functions. Let me show you one practical, again, example where we have used Me resonators and arranged them over a large area to make a device, in this case, to try and do water splitting on a large scale with iron oxide. And this is, in general, a challenge. Here's a list of ideal traits of a photocatalyst for water splitting, but this is in general very similar for all light-driven catalysis experiments. There's a list. You would like to have a high efficiency for the chemical process. You would like to be the materials to be earth abundant. You would like to have them be chemically stable. They need to have the right electronic band alignment. Many things need to come in place, and people have tried to do computations to find ideal candidates. And here is a computational study that you should not be able to read, but here are a whole range of different elements on the horizontal and vertical axes, and these are oxides made of these elements, and only a few of them here have some of these desirable properties. What I want to tell you is that many can be coming in place, but one key challenge is to get very strong light absorption near the surface of materials. For example, iron oxide, rust, has many of these desirable traits, but it's a very poor light absorbing and poor charge transporting material. So I'm trying to argue that actually photonics can help fulfill some of these many requirements. And to illustrate how that might work, I have a simple schematic here of a chunk of rust, water on top. If I want to drive an oxygen evolution, water splitting reaction, where I come in with light, generate electron hole pairs in the rust. In this case, the rust needs to, inside the rust, the generated holes need to make it to the rust-water interface where they can drive the oxygen evolution reaction. But this is challenging because the light that comes in green exponentially decays into the material, and the absorption depth of light in iron oxide is very long, typically microns above the band gap, whereas the diffusion length of the hole is just 10 nanometer. That's plotted over here. There's the propagation depth of essentially the light in blue and the carriers here in red. So over a very broad wavelength range, the diffusion length of the carriers is much shorter than the absorption depth. So none of the carriers that are created can make it to the surface where they can derive the valuable reactions. So high index nanostructures come to the rescue. We could make beams of iron oxide, rust. If we can shape them in different ways, then not only we can resonate light inside to boost the overall light intensity and absorption per unit volume, but we can also shape and engineer where the light fields are the strongest, hopefully right near interfaces of the iron oxide and the water, so that the valuable photo-generated carriers can make it out. So here's one, I guess, short version of this story. We try to go away from smooth iron oxide metal surface, but we shape them into arrangements of little beams. And if you do that, you can see that if you compare the field intensity in one of these beams in cross-section versus a smooth iron oxide interface, that you can significantly enhance the light field intensity right at the interface between the iron oxide and the water, and you can prove that this will help you indeed enhance the water splitting reaction just by putting one of these samples, where here's a cross-section of a beam array, here's the iron oxide, size big enough to support me resonances, to stick them in a photoelectrochemical cell, and in this case you see the Venn diagrams of the iron oxide and the water next to it. With light, I can generate an electron hole pair. The hole can drive the oxygen evolution reaction. The electron goes through an external circuit where we can measure the rate of reaction if we believe there are no other reactions, and thus we can use to see how quickly the reaction goes in a sample where we have beams and a sample where we don't have beams. And what you can see is in the measurements, if you plot the photocurrent enhancement for a sample with a structure with beams versus a smooth sample, is that we get a significant enhancement right at a frequency where our simulations predict that we have a me resonance. So we can tune where we get light absorption most effectively, and we can also engineer where that light in the structure is absorbed to make this type of process better. The last example that I want to show in terms of light absorption is one where we're going to look at the ultimate limits of absorption in a very thin film of material. And this has been studied by many pioneers. Here's the work by von Woltersdorf, who showed that if you have a very thin metallic film of the right sheet conductivity, if you plot the absorption versus sheet conductivity, you see the absorption, this curve over here, go exactly up to 50%, a fundamental limit for a free space floating metallic film. And Salisbury later showed that if you put a very thin conductive layer behind a back reflector, or in front of a back reflector, you can get 100% absorption. And this work recently got a lot of attention again from the work of Federico Capasso, who showed that if I deposit very thin layers of germanium on the order of 10 nanometer then I can get very strong light absorption, and depending on the exact thickness, whether it's just a nanometer thicker or thinner, I can tune the color of samples that have, in this case, germanium on gold, all around the visible spectrum, and get very strong absorption. Basically, the color is here a signature that you can achieve very strong absorption at a target wavelength. But it turns out that it's an interesting question to see whether you can enhance the broadbandness of the absorption. Right now, the fact that they do see color at some wavelength means that some wavelengths are being reflected. Well, we did an initial study. This is a theoretical study of the absorption as a function of wavelength, where we placed germanium on silver. And you can see, interestingly enough, that this is the absorption, the green line of a thin layer of silver of just 12 nanometers, absorbs quite a bit because of the strong absorption properties of germanium. But if I put that layer on silver, I get this curve over here. There are actually two curves over here. About one is all of the absorption that happens in the germanium, up to 98% at the peak wavelength, and 2% of the light absorption happens in the metal, totaling exactly this limit of 100% if I perfectly impedance match, in this case, to an incident light wave. But you can also see, although I get very broadband absorption over a couple hundred nanometers above 80% or so, this is not everywhere. It is nice to see that this is the absorption directionality, that the absorption in such a thin is extremely omnidirectional. So it would be very interesting to be able to make solar cells or very thin detectors that can absorb 100% of the light in just about 10 nanometers. The question is, can we tune it to be more broadband for example, solar applications? Well, to think about how we could tune it, one might think about a simple case where simple model first to gain intuition how this works. And here's the very simple model. Light can come in, hit the germanium film on silver, and what can happen is that the light can reflect off of the first interface, or it could go inside, circulate around a little bit, and come back out. Well, if these two pathways are equal amplitude and exactly out of phase, none of the light can come out, and you get perfect absorption in the film. Okay, that can happen if you have the right materials properties for your germanium. But what you see in this case, if I now try to, for example, tune the absorption, maximum absorption to another wavelength, then the peak of the absorption can move if I make my film thicker, but actually the amount of absorption at the peak decreases if I had more germanium. Sounds unusual. If I have more material, I get less absorption, but this is simply due to the fact that I disturb my delicate interference condition that allowed me to get perfect absorption. So we need to do something else. We can't just tune one geometrical parameter, and this is something else is we can break up the germanium film into a series of resonant beams that we've learned some about today. And here you see an SEM image of a beam array. I'm going to talk about beam arrays here in the lighter color of germanium. You can look through the beam array. We've etched away the material in between, and the scale, the distance between beams, is sub-wavelength. So it's a metamaterial. I don't produce higher order diffracted orders. And I can see a big change in the optical properties in optical microscopy of the gold here in the background. A thin, this is 50 nanometer germanium film lying on top. It's quite reflective. And here I have two images where I have one polarization transverse electric with the electric field normal to the length of the beam, and here transverse electric with the electric field along the beam. And I'll try and argue that in the case of TE, I don't drive a resonance, and the light actually just sees the gold. That's why this looks at dark gold, gets a little bit of absorbed. In the TM case, I can drive a resonance in the beam, and almost all of the light gets absorbed. That's why it looks black. So here's detailed images of the power flow inside the structure. Here's the fields real part of the electric field. You can see the wave coming in. Here's the flow lines, and you can see the flow lines, many of them hit wires, but also a lot of them flow lines, the power flow hits the gold where it gets absorbed or reflected. And you get a very standing, if you look at electric fields, you get a very strong standing wave pattern due to the fact that a lot of the light reflects back. If I look at this case, the power flow, then I can see light comes in very close to the wire. I have an antenna effect due to the resonance in the silicon beams, and at the last moment, right below above the surface in the near field, the power flow gets redirected into the beam to drive this resonance inside the beam. It's not a very high Q resonance. The Qs are typically 1, 2, 3 in these examples, but with the strong absorption of germanium, the only thing that I need to do in this case is to let the light flow into the germanium beam and be absorbed to try and achieve impedance matching. And you can see that the standing wave profile here in red has become almost constant as most of the light is absorbed in these beams. Now, one interesting thing is that this leads to an opportunity to drive these resonances. Here I plot the absorption that I derive from a reflection measurement versus wavelength. And I see for one specific sample here that if this is where the beam width have 60 nanometer spacing and a 1, 2, 3 filling fraction of germanium to air, I see a nice peak, and interestingly the resonance of the peak, where I get the strongest absorption, nicely matches this vertical line, which is the resonance wavelength where one beam on the metal back reflector would have absorbed. So the metafilm, composed of many beams, absorbs exactly strongly at the location where one beam strongly absorbs. And if I do this for other widths, for example, in blue, a 30 nanometer, green 45, and yellow 60, I can tune the maximum absorption peak wavelength just by changing the width of the building block. So by making narrower beams, I can tune the wavelength to shorter wavelength, and this is maybe intuitive if you have a very resonant beam-focused view of life, because the resonances are exactly where the individual beams resonate. But if you're thinking about metamaterials theory, a first-order effective medium theory says the only important thing here is the filling fraction of germanium and air and the dielectric properties of air and germanium. In this case, the filling fraction is the only important thing. And interestingly enough, in this experiment, we actually kept, while making the beams narrower, we kept the filling fraction the same. So we're in the regime here where the individual blocks dominate the optical response of the metamaterial, not an averaging of the permittivities. So that means that our knowledge of individual beam resonators is very important and useful in designing these metamaterials. There's a whole different way the power flows into the structures. If I have a resonance, then I have antenna resonances in the beam. I collect light from a large cross-section, funnel it into the structure. If I look at the field profile, I'll get strong resonant features. If I go to the deep subwavelength regime, so small sizes keeping the same filling fraction, that the resonance has to disappear due to near-field interactions, then the field slowly becomes continuous. So this is the gradual change from a resonant, if you like, metamaterial to a non-resonant one. And you can see this nicely also in a plot of the absorption in colors. Red means strong absorption, blue very weak absorption as a function of the wavelength, and here's the width of the beams. And this is an experiment or a simulation where we move with a constant filling fraction. So that means that I can associate for every width a period. So if we now, on this somewhat complex plot, identify where an individual resonator would have the strongest absorption, that's this dashed black line over here. And you can see that as I follow this dashed line, as soon as I place these beams close to the diffraction or to the grading limit, where I now have quenched out, the period has become so small that I can no longer generate diffracted orders, first order diffraction, then I've generated a metamaterial, and immediately the absorption goes up to very close to 100% if I do this arrangement with resonant beams. And as I make the beams smaller and smaller and move to the left, then I see that my peak of strongest absorption moves to shorter wavelength. Smaller resonators absorb more strongly. But ultimately, the peak of the absorption of the metamaterial here in red deviates from where the individual resonator would absorb, the dashed line, and it moves to this line over here, the dashed blue line. And this is exactly the prediction where a subwavelength, deep subwavelength array of resonators would most strongly absorb based on the Fabry-Perot resonance. So interestingly, this regime over here, and the blue dots are simulations, there's a large range of beam sizes, maybe from 50 to 250, where the absorption, spectral absorption properties are fully governed by the geometrical resonances of the beam, and not just the filling fractions. So this is a very interesting area. There's an even more exciting opportunity, that is, one can use these resonances to enhance the broadband absorption in the layer, and that's shown here. Note that if I plot the power flow into the array of beams at a wavelength where I have almost unity absorption, note that I have these resonant effects, where antenna effects, where light can be funneled in from a large area into small beams. But there's now geometric space between the resonators. So I could put in smaller resonators right between these beams. And if I put some smaller ones in between, note that the power flow at this wavelength is hardly affected. However, if I move to another wavelength, where the small beams are resonant, they suddenly can grab a lot of extra power that wouldn't have flowed into this surface if I didn't interleave the small and the big beams. So you have an interesting opportunity, because the cross-sections, optical cross-sections, are big of these resonator structures, to start interleaving geometrically many resonant structures to manipulate the absorption spectrum. And here's an example where we've made samples with just big beams and small beams, and interleaved big and small beams. And you can nicely see that the absorption spectra of these structures look like a linear superposition of the resonant properties of the individual ones. So here's a reflectivity spectrum versus wavelength experiment, and simulation on the right matches quite nicely. You can see the reflection spectrum for just the big beams shows very strong absorption on the long wavelength side. Just the small beams shows very strong absorption at the short wavelength side. And if I interleave them, I can get very strong broadband absorption over a very large wavelength. So in this way, I can start artificially engineering my absorption spectrum. If you give me semiconductors based on a desirable electronic or mechanical or other property, now I can start interleaving them and tune my exact spectral properties with whatever semiconductors you like, and this may have some applications in optoelectronics. To really drive home that you can tune them individually, the absorption features are shown here, where on the left and right we look at the absorption spectra, where we just change the size of the small beam and leave the big beam the same, not moving the big resonance, and here we just tune the size of the biggest beam. So I want to close with one last image. I'm told I should finish up, and that is a very complex arrangement of dielectric resonator structures. So here's a structure that most recently we started working on. It has about 20,000 different silicon beam antennas, and there's a gradient in the orientation of the silicon beams. And by making gradients in the orientation, size, or shape, we are now able to manipulate wavefronts, and there are a number of groups that are actively working on this. And this is the last picture I'll show you, where we take such an arrangement, come in this case, with a circularly polarized beam, and make this arrangement of antennas to perfectly work as a tiny little hexagon. So there's a whole new set of building blocks that we can use to manipulate light absorption, reflection, beam shaping, and hopefully in future also move this into an active regime. Thank you for your attention.